Okay, welcome to the Chapter 2A review. Chapter 2A began our study of derivatives. When we talk about a derivative, we could define it informally as the slope of a tangent line to a function or a curve. We could also describe it as a rate of change. When we talked about derivatives, we talked about them in 4 different ways. We described derivatives with the written word. And when we did so, we referred to it as the rate of change. Right? We described derivatives also graphically. We talked about derivatives graphically. We were typically talking about that slope of the tangent line that was previously mentioned. Take a look at a graph, any given curve, f of x. We could talk about the slope of a tangent line at a certain x value. We draw a tangent line and literally find the slope. Right? Third way we talked about the derivative was analytically. When we say analytically, we're talking about equations. We could describe a derivative as f prime of x. Derivatives are functions typically. Derivatives can be known as functions. And we can take those functions and plug in x values then to find the actual slope of the tangent line at a point. So a derivative function could possibly be x squared plus 4. That derivative function is simply waiting for an x value to be plugged in. When that x value is plugged in, you will have the slope of the tangent line at that x value. So analytically, we're talking about equations. Numerically, when we say numerically, we're typically talking about a data table. You're given x, you're given an f of x, you're given data. Perhaps x moves in increments 1, 2 to 3, and the function perhaps, say 4, 7, and 13. We could be asked to approximate the derivative at one of these x values. Perhaps we're asked to approximate f prime of 2. If so, we have 3 different options for our approximation. We could find the slope between 1 and 2. We could find the slope between 2 and 3, or we could find the slope between 1 and 3. All will give us correct approximations. Let's choose 1 and 3 for example's sake. We're using the AROC formula in this case, the average rate of change formula, between 1 and 3. So the secant slope formula, it's also known as f of 3 minus f of 1 over 3 minus 1. F of 3 is 13. F of 1 is 4. 3 minus 1 is 2. 13 minus 4 is 9. So we have 9/2 as our approximation of the derivative when x equals 2. Next was the formal limit-based definition of the derivative. We define the derivative, f prime of x, as the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Coming out of our limits chapter, we learned how to evaluate these limits longhand. You will not be expected to do that in the AP exam. In fact, these should be very quick and easy problems. You should recognize the form of this limit as a derivative question. There are multiple forms of the limit-based definition of the derivative. One form uses h's instead of delta x's. For example, finally evaluate the limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. solve this problem, we should recognize that this is a derivative question. We are being asked for the derivative of cosine. Our answer will be an equation. It will be a function. The derivative of cosine is negative sine of x. If, by chance, we were asked a slightly different question, where instead of x, we were given pi over 3. So in this case, we are asked the following question. We are asked to first evaluate the derivative of cosine and then plug in pi over 3 to our derivative. The sine of pi over 3 is root 3 over 2. So our answer will be negative root 3 over 2. Just a couple quick reminders. If a problem is given in a contextual situation, typically terms like rate of change are being used. If so, you ought to always remember that your answer should include its units. If we are talking about a derivative as an answer and you have a numerical answer, you would have your number or numerical answer and then its units. One of the most common problem types that we saw was the position, velocity, acceleration problem. If you are given a position in meters, and then asked to find the derivative of position, which is velocity, your unit would then be meters per second, typically, if we're working in meters and second. AP has a tendency to use other units. They will use feet. You will see hours as well. Typically, these will be contextual problems that we can't make up off the top of our head. So be prepared for anything. Be prepared to use your slope units as the units for your derivative. When we talk about derivatives, symbolically f prime of x or dy dx, we can get a series of answers. You could get a positive number. We get a positive number, we're simply saying that the slope is positive, or the function is increasing. We get a negative number, we're talking about a negative slope or a decreasing function. If we get 0 divided by a number, 0 divided by a number is simply 0 or a constant function at that point. If at a certain point we get a number divided by 0, we're talking about one of the DNE cases. The function at that point is vertical or has a slope of plus or minus infinity, an undefined slope. Therefore, the derivative is said to be DNE. If we get 0 divided by 0, again, this is an undefined DNE situation at that point. Don't forget about average rate of change and instantaneous rate of change. When we talk about average rate of change, we are talking about a secant slope. A secant slope is the slope between 2 points. It's your typical geometrical slope formula. Don't forget to write the formula out. In this case, we'd be talking about f of b minus f of a over b minus a. as the average rate of change. When we talk about instantaneous rate of change, we're talking about our good old-fashioned derivative at a point, or f prime evaluated at c for IROC. IROC could also be written as the limit as the denominator approaches 0 of any AROC function. If we were to take the AROC function that we used on our left and rewrite it as an IROC function, we would do so by taking the limit as b approaches a of f of b minus f of a over b minus a. By taking the limit as b approaches a, we are allowing the denominator to approach 0. Remember, there are multiple versions of AROC. Multiple ways to write AROC. Multiple ways to write the limit-based definition of the derivative. IROC is simply the limit-based definition of the derivative evaluated at a point. We could be asked for a written description of a derivative. We may be given s prime of 3, or the position at 3 hours. Rate of change of position at 3 hours is 17 miles per hour. If so, we could be asked to describe that. When time equals 3 hours, the rate of change of position with respect to time is 17 miles per hour. Don't forget to acknowledge the moment in time when we are referring to this particular rate of change. Don't forget units as well whenever necessary. We developed a series of shortcut rules. Those can be found and listed on page 173 in your textbook. We shifted our focus then to the chain rule. We attacked the chain rule in a few different ways, two of which I'm listing here, analytically and symbolically. Let's talk symbolically first. If we're given a function h of x, which is equal to f of g of x, in other words, there's a function g of x embedded inside the outer function f. We apply the chain rule to find the derivative, h prime of x. The general method of the chain rule is to work from the outside in, taking derivatives, leaving the inside alone, and multiplying along the way. So our outermost function in this case is f. So we'll derive f prime. We will leave the inner function, g of x, alone. Still inside f prime. Now that we have dealt with f, we will multiply by the derivative of the inside, or g prime of x. That would be the symbolic derivative of h of x, or h prime of x. Analytically, or equation based on the right, we have j of t equals tangent cubed of 4t. It's important to recognize that the outermost function is a cubing function. So in solving for j prime of t, we will first take the derivative of something cubed. The derivative of something cubed is 3 times that something squared. We will then multiply by the derivative of the next outermost function, which in this case is tangent. We have already dealt with the cube. The derivative of tangent is secant squared of its inner function, which is 4t. that we have dealt with the tangent. We are left to deal with 4t. The derivative of 4t is simply 4. And that would be j prime of t. Finally, one of the most common free response questions that we'll see on the AP exam, typically see one per year, is a position, velocity, acceleration question, which involves both derivatives and integrals. From the derivative standpoint, we have the following. Velocity is a derivative of position. Acceleration is the derivative of velocity, or second derivative of position. It is common to denote left and down as negatives, and right and up as positives when referring to a particle moving. We typically are given a function with a particle moving along the function. Common questions are to be asked when the acceleration is greater than 0. Another common question is to be asked when the particle is moving to the right. To be moving to the right means that the velocity is positive, or v of t greater than 0. There are many more question types that can be asked off of position, velocity, acceleration, many of which you will practice in the coming weeks. This concludes Chapter 2A review. As you know, we track your views of this content to prove to your teacher that you got all the way through to the end. Give them a high five when you walk in the door tomorrow morning. Thank you and goodbye.